can you give me some example of if a wormhole exists out there, and I know we don't know if they do or not, where will they be? What will they be near? What will have had to have happened for one to have spontaneously existed?
Oh, Brady. Okay, so we don't know. That's one of the big problems. There is no decent mechanism to form wormholes. They are solutions. They are, in other words,
Solutions to what?
to Einstein's equations. So what does Einstein's equations do? It's got a left-hand side and a right-hand side. That's what all equations have. On the left-hand side of the equations are terms that involve the curvature of the space, how it's bending. And on the right-hand side are terms involving what's in that space, the matter content, the particles that you and I might be made of. For a wormhole to exist, you generally need some sort of rather extreme combinations of things in order for them to be stable, and that's why you need these, for example, negative energy particles. But we don't have a mechanism to actually form them properly. In other words, we don't have a situation where, at 2 o'clock in the afternoon there isn't a wormhole, and that 1 minute past 2 a wormhole has been created. There isn't a nice phase transition, for example, which takes you from no wormhole to a wormhole. The one possibility that has been put forward that suggests that there may be wormholes there, but this sort of gives you an idea of how exotic you have to be. One of the objects that we believe may have been present in the early universe, and we should actually probably do something about it, is a cosmic string. Cosmic strings they're called defects. They're line-like defects, a bit like cracks in ice. When water freezes to ice, it sometimes has these cracks, discontinuities in them. The cosmic string is an analogue in the very early universe. Now, if those cosmic strings are made of this substance which has got this negative energy, then it's possible that at the end of the cosmic string, there could be the throat of a wormhole. And then as that cosmic string expands, as the universe gets bigger and bigger, that throat gets bigger and bigger, and it's stabilized because it's connected to this negative energy region. And so but for that to have occurred, that would have to be there in the very early universe, the first 10 to the minus 35 seconds of the universe, and still be present today. There is no mechanism I'm aware of that just creates wormholes for us and then just pops them, they then disappear again on you. They're either, the solutions just say they're there, but they don't tell you how they got there. You need some extra ingredients to do that. So that's one of the problems.
I always imagined wormholes as these things that I could jump in here and get dumped out near Neptune or Andromeda or wherever. And that's always explained, by bending pieces of paper and touching bits of paper. Well, how does time come into this? How can time travel be possible in a wormhole? I thought it was a geographic thing almost.
Yeah, sure. So you go from one place to another. The reason why time comes into it is because the thing that's being bent isn't just space. It's space-time. It's a 4-dimensional thing, 3 space and 1 time. So you can bend it in such a way that the actual thing that's been affected is the time. And in fact, we could be sat in this room, and if I've got my wormhole solution right and find the right wormhole, I could project us forward to an hour from now, and we'd probably still be talking. But it's because it's space-time. It's not just space. Back in the 80s, when the work of Kip Thorne and Morris and Stephen Hawking was doing lots of work, when wormholes became really fashionable, people were dedicating themselves. In fact, at the time I was a postdoc in Fermilab, and I remember we had a series of talks. We decided to teach ourselves about wormholes, and we had a series of talks that went on for 6 or 7 weeks. As we tried to read all the papers that were coming out, people were really excited about them. And then people move on. It was realized that, first of all, you need this very exotic matter for them to be stable. And then there's the question of their stability against this feedback mechanism, and other things took over. But people have carried on working. I don't think they are working full-time at it, but really significant players like Kip Thorne have made massive contributions over the number of years to this field, as has Stephen.
So people talk about wormholes as useful things of the future. That's ridiculous, is it?
Never say ridiculous in this fantastic kind of fun area. Yeah, you can say it's ridiculous, but never say never. Clearly we haven't got the technology at the moment to do anything like this. But the idea of travelling in time, I think, we already can do it. Maybe not through a wormhole. I don't know if you're aware of that. I think the idea of having a wormhole may be just that little bit beyond us. But the idea of travelling in time isn't out of the question. We can travel forward in time because of relativity. Relativity tells you if you're in a spaceship and you're travelling sufficiently fast, your own clock slows down. And so it's possible, if you could go fast enough, then you could reach, say, a distant planet or a distant galaxy in a finite amount of time, such that you could survive, and then we can maybe repopulate distant planets. So this is, is talked about by many people as something of the future. The problem is to get the fuel sorted and to get the technology sorted so that you can actually travel fast enough. But we know in principle it's possible.
Who called it a wormhole? Where did the name come from?
The wormhole was from John Wheeler. John Wheeler, and his idea, why a wormhole? He thought of a worm tunneling through an apple and realising that was the quick way to go from one side of the apple to the other side of the apple, hence wormhole.